So this is lecture 4. So in last 3 lectures we have discussed what are the different types of feedbacks, and also we discussed in detail the closed loop control system, the effect of feedbacks in closed loop control system. So that we have discussed, that is the closed loop control system. So let us first draw it. So that is, we give one reference command R here, and this is that controller, and the control input is fed to the plant. So this is that plant, and we take feedback here. So this output, this is called that controlled output, and here this is that control input, and E is that error signal. So suppose we are taking that negative feedback. So here that error signal E, that equal to R minus Y. So the idea of feedback, to make corrective actions, so these corrective actions means, here this corrective actions is basically this U, that control input, the output of that controller, based on the difference between the desired and the actual values. So here you can see the difference between the desired and actual values. So here R is actually the desired values and Y is that controlled output. So this difference means here actually that error signal, the difference between the desired and the actual values, that is that error signal of a quantity can be obtained in different ways. So that means the control input that you will be generating, it can be done in different ways, and today we will be discussing two types of control. One is that on-off control, and other one is PID control. So this PID stands for proportional derivative, proportional integral and derivative. Integral and derivative. So this particular control input controller is widely used in industry and everywhere, and also this on-off control, this is the simplest form of feedback control which has many applications, like that in refrigerator, in air conditioner. So everywhere we use this on-off control. So today we'll be discussing in detail, that means how that on-off control works. So let us start this on-off control strategy. So here you can see that reference command we have given, and we want that control output should track that reference command. So then an error signal is generated. So this error signal is actually the difference between that R and Y. So now this on-off control strategy is as follows. So let us first just draw only that part, that comparator part. That means here we have that positive, this is the command signal. We have that command signal, and here we have that controlled variable, that is that Y. So here you have that Y, and we are using negative feedback. So here you have that E, which is actually that error signal. So now we have that controller, which is on-off controller. Now depending on this particular error signal, that on-off controller generates some control input, that is U, which is actually that, this U is actually that corrective actions, which is fed to the plant. So now what is that control law? This control law is the simplest one. This is the simplest form of control law, that is U equal to U max whenever error equal to is positive. That means error is greater than 0, and this is equal to U min if error is less than 0. So this is the simplest form of controller, and here you can see this error signal E equal to R minus Y, that we have already discussed. So now just from this particular structure we can understand that this is that the control strategy is very simple. So this is a simple form of controller, and we have not chosen any parameter to get this control output. This control output U depends only on the error signal E. So no parameter to choose. So that means to generate this control input, we need not to choose any parameter, because it only depends on the error signals. When error equal is positive, then U equal to U max, and when error is negative, then U equal to U min. And it has some disadvantages as well. So one disadvantage is typically it results in oscillation of controlled variable. So this is obvious. The reason is whenever error is changing, once it is becoming positive and again it is becoming negative, so U is changing from U max to U min, U max and U min, and there is a discrete jump. So there is an oscillation in controlled variable. So this is actually one of the disadvantages of on-off control. The reason is, if we are interested in to get a smooth output from on-off control, we cannot have it. So how it looks like? So suppose this is the t-axis, and here you have that control variable yt, and suppose you have set that reference command r here. So now whenever that output is increasing like this, suppose that output is increasing like that, and whenever this y crosses that r, so that then you can see here, from here, whenever y is greater than this r, then obviously that error signal becomes negative, and whenever error signal is negative, u equal to u mean. So immediately you can see that, so that u mean, if it is equal to suppose 0, suppose u mean equal to 0, so that means whenever that y crosses that r, when this y crosses that r, so if u mean equal to 0, so that means there is no control input, that means it is in off stage. So whenever it is off, then immediately it starts falling down, and when again y crosses that r, that means error is positive, then again it is on. So like this, that means the output, there will be some oscillation because of that on-off structure of that controller. But this particular control strategy is very much effective. As I have pointed out, this control is used in many cases in industry anywhere. Like for example, this on-off control is used in refrigerator as well as air conditioner. So you can find many examples where this on-off control strategy is used. So there is another disadvantages of this on-off control, although it is simple, that is control variable, because you can see here, whenever that error equal to 0, when error equal to 0, so no control input is defined. So you do not know what would be the control input, how much input will be fed to the plant, how much control input will be fed to the plant, you do not know. So this is one of the disadvantages of this control strategy, but as it is very simple, it is also an effective control algorithms. So one thing is that control variable is not defined when the error is 0. So to overcome these advantages, some other control techniques are also used. So here I am just showing, that means how that on-off control works. So this is that error signal. So, and this is that u. Whenever error is positive, then you have some value, that is u max, and whenever error is negative, then you have u min. So when error is negative, then that control input equal to u min, and when error is positive, then control input equal to u max. But you do not know at this particular point, that means when error equal to 0, what value you have to take. So this is actually that on-off control strategy. So similar to on-off control, there are also some other strategies like that, very similar to this. Another one is called the dead zone. So this is error. So in this case, what happens? So this is that control input U. So whenever error equal to 0 or error equal to 0 or error is positive, that means suppose this value is E max and here this value is E min. So that means when error is inside that band, so this band is this one, then there is no control input. So in this particular band, that error control input equal to 0. So when error in between E max to E min, then control input equal to 0. So this particular zone is called that dead zone. So this is called dead zone controller. So that means we are allowing some dead zone here when there is no control input U0, but when error greater than E max, then immediately we apply U max. Similarly, when error less than E min, then we apply U min. So that means the difference with this dead zone and on-off control is that in case of dead zone, we just allow one zone, allow a band. Whenever that error lies inside that band, then control input is equal to 0. So this is also another type of control strategy we apply in practical applications, and the name of this one is dead zone control. Sometimes we also use another type of control strategy that is called that hysteresis control. So in that case, we just keep some overlap. So the overlap is like that. So suppose you have started from here, say suppose error is increasing positive, so then it is 0, and whenever error is coming say E max, then suddenly it jumps to this value, and suppose error is increasing, it is going like this. But what happens whenever error is decreasing, suppose error is decreasing, so then it follows this path. Instead of jumping here, it follows this path. And then whenever error equal to say E min here, then it jumps from this point to that point. Then again suppose error is increasing, so when error is increasing, it follows this path and finally it jumps here. So that means whenever suppose your error is this one, say suppose error E star, then you may ask a question, what would be that value? So it may take this value or it may take that value. Yes, you are correct. But you know whether you will be here or at that point, it basically depends on your initial condition. Suppose you know you have reached at this particular point just by increasing this error from this side to that side, that means you will be at that position. So whenever suppose you are here but you have reached this particular point just by decreasing this value, that means of course you will be following this path, you will be here. So that means it depends on the initial condition. It has some memory. So this type of control is called that hysteresis control. So hysteresis control is very, very effective, but there is a problem as it has some memory and it depends on the initial condition. So in all cases they impose some sort of nonlinearity, but for these types of nonlinearity and for these types of things it is very difficult. But as we are discussing today only the controller, we are not discussing hysteresis nonlinearity, which is very common in all dynamical systems. But you should not be confused with that hysteresis types of nonlinearity and the controller. So here actually we are talking about that hysteresis control strategy, and in this case we just allow some overlap. So let me summarize the three different types of control strategies. We have discussed that on-off control strategies. So in on-off control strategy, actually, what would be the control input when error equal to 0? You do not know. It is undefined. So it actually works in on-off mode. So whenever error is positive, you are at control input is U max. When error is negative, the control input is U min. Now, in case of dead zone nonlinear, in case of dead zone control, so we allow this overlapping zone. Whenever that error is inside this band, then this control input equal to 0. But whenever this error goes beyond this E max, then it jumps to that U max. And similar thing happens in the negative side. And in case of hysteresis, actually we just allow this overlapping zone, and it follows this arrow lines, and this particular control strategy is very effective, and in many practical applications we use these type of simple control strategies. So now one thing is very much clear to all of us, that this type of control strategy, if we use, then that control variable, it should not be smoother one. That means there would be some sort of oscillations. So how can we make it smooth? So to overcome those problems, we actually use, say, PID type of control strategies. And another thing also is important, and also I'd like to mention. So in case of on-off control, you can see here, if a little bit error occurs, say suppose error is very small, that means say 10 to the power say -5, very small. So even if that error is very small, you know that control input immediately jumps to U max. That means this on-off control actually overreacts. So this on-off control overreacts. So to overcome these disadvantages of those control strategies, we use that PID type control. So let us start discussing on that PID control strategy. So PID control. PID control. So PID control, it is proportional, integral, and derivative that I have already mentioned. So here I can also point out that better to elaborate these things, that is a small change in the error makes the actuated variable, that means that U, actuated variable, that is that U, change over the full range. So that means if error is a small value, if only small error occurs in the closed loop control systems, that control input actually becomes U max or U min. That means that overall changeover occurs. So it actually overreacts. So to overcome that particular disadvantage, so we use that proportional control. So the above disadvantage. So that above disadvantage can be avoided in proportional control. So how it can be done? So let us first write the control algorithm for proportional control. It is very simple, like one of control, that is U equal to U max if E greater equal to E max, and U equal to Kp into E if error is less than E max and greater than E min, and it is equal to U min if error is less than E min. So here this Kp is called that proportional gain. So this Kp is the proportional controller gain. So that means if we just draw it, it is very simple, that you can also do it on your own. So this is that error signal, and here you have E max, and here you have E min. So basically so it looks like that. That means whenever so this is that control input U. So that means whenever your error is inside this range, so basically instead of keeping U equal to 0, that means in case of dead zone control, what we have seen, we keep U equal to 0. But in the case of proportional control, what we are doing, we are just generating one U, which is Kp into E. So now what would be the slope of this control law? It depends on that how much control gain you have chosen. So this Kp is actually that controller gain, and as a designer your job is to design this Kp. So the interval E min to E max is called the proportional band. So now what is the drawback? So the drawback is you can see here whenever that error becomes 0. So whenever error becomes 0, E equal to 0, then this KPE that would be equal to 0. So when control input equal to 0, so then immediately that control variable will be shifted from the desired value, and whenever that control variable is shifting from the desired value, that means we would not achieve that tracking performance. So that is a big disadvantage of proportional controller. In case of proportional controller, we cannot achieve that perfect tracking performance. That means that control variable deviates from the reference. So in order to maintain it, so that means whenever the output y, that means that control variable cracks that reference command, then error would be equal to 0. So when error equal to 0, then the control input u equal to kp into e, that would be also equal to 0. So then immediately it deviates. So that means in order to generate some control input, you cannot make error equal to 0. That means you cannot have the tracking performance. So in order to maintain it, E should not be equal to 0, since some control input is required. Some control input is required, that just now I have pointed out. So this is a big disadvantage of proportional controller. So this is, I would say, this is drawback. Drawback of proportional controller. So how we can overcome this particular drawback? So this can be avoided by making the control action proportional to the integral of that error. So let us see what is that. So this can be, this means this drawback, this can be avoided by making the control action proportional to the integral of the error. Let us see. So that means the control input ut. So the control input means, here you can see here this control input ut. So basically we are just trying to make that ut is equal to integral of e dt. So in case of proportional controller, what you have done, u equal to only kp into e. But in case of integral control, so this control is called that integral control, as that integration is involved. That control input is generated as the integral of that error signal. So I hope you understand. That means what are the different types of control algorithms can be applied or can be generated to achieve some sort of performance. So here we are just discussing the tracking performance. So this is that ki 0 to t e tau d tau. So here this is that error signal, and this ki is called that integral control gain. So integral control gain. So as a control systems engineer, your job is to design what would be the integral control gain. So in case of proportional controller, your job was to design this proportional control gain. In case of integral controller, your job is to design this integral control gain. So I think from these control strategies, it is very much clear to all of you that these control structures are very simple but very effective, because already in last class we have solved some problems, and today I will be asking you to solve some problem in MATLAB. Then you can see how we can achieve different types of performances just by using these simple control strategies. So in this particular case, so let us see, that means how that integral control works. That means whenever you have, suppose, error signal, suppose you have taken some constant error signal. So whenever you have that constant error signal, so suppose this is 1, and then what would be that u, because if you just integrate it 1, so that would be that ramp signal. So that means ut, the output of that controller, it would be equal to that ramp signal. So now this slopes depends on, that means what ki you have chosen. So in this particular case, the big advantage of using integral control is it gives you the tracking performance. That means the steady state error. So this particular term, for the time being, you just take this term. I will be discussing this one in detail later. So the steady state error becomes 0. That is a big advantage of using integral control, because in proportional control already you have seen the drawback of the proportional control. It cannot give you the 0 tracking performance. The reason is whenever e equal to 0, that means output tracks that reference command, then there is no control input. So proportional controller cannot help in this regard, but in case of integral control, it actually helps you to achieve tracking performance. You may ask how. The reason is whenever this error signal becomes 0, as you know, the integration of that 0, it will be giving some biased terms, some biased values. That means even if that error signal equal to 0, there will be some control input that would drive that whole closed loop system. But in case of proportional control, when error equal to 0, that means ut equal to kp into e, that output error control input would be equal to 0. That means there is no signal that can drive that system. But in this case, that integral control helps. So now you may ask one thing, that why we are not using that proportional and integral controller together. Yes, we can use it. So this particular control is known as PI control, that is proportional integral control. So proportional integral control, that means in this case we will be using proportional and integral control together. So how it looks like? So suppose you have that error signal ET equal to 1, and this is your time axis. So now what would be your PI controller's output? That means the proportional controller is actually kp into e. So that means depending on your kp value, it would be this kp. So this is actually proportional, and integral part you have seen, integral controller would give this output. So whenever you use PI control, that means p plus I. So proportional will be giving this output, and integral will be giving another output like this. So now as it is p plus I, so the effective output is this one. So this is actually PI output. So this is UT. So that means in closed loop control, so if you use a PI controller, that means P plus I will be showing you that block diagram. So how it looks like, that means error signal is coming here, error signal ET, and then it has two blocks. One is that Kp, the proportional block, and another one is that integral block, that means that integral controller. Now if you add the effects of proportional and integral, then the effective output you will get, that is ut. So in this case, this ut is this one, that is that ut. So I hope it is now clear. So in control, we also use the different types of structure which is called the derivative control. So that derivative control is actually works in anticipative manner. That means it can anticipate, that means what would be that error it may face. So depending on that error, it actually generates some control input in some time advance. So let us see what is that. So an additional refinement here we can do, that is we can provide another control structure where that control input depends on the rate of change of that error signal. So that means here I am writing an additional refinement is to provide the controller with an anticipative ability. That means if your controller can, if it can anticipates, that means what error may appear. So accordingly, if it can generate some control input, so that the transient response as well as the performance of that systems can be improved. So by using a prediction of the error, so that is E t plus td. So this is just simple derivative. So that means Et plus Td. So this is actually the time, and this is that error signal. This is that error signal. So Et plus Td minus Et divided by Td. So if you put limit t tends to that, Td tends to 0. So that means that would give you, that gives you that derivative of that error signal. So here we can see whenever you have that error signal here et, so suppose error signal is a ramp signal, and here I would like to mention one thing. So this type of control strategy only works in the transient part, because if error is constant, so then this term would be equal to 0. So that means whenever error is varying, then only the derivative action takes place. So here you have seen that it predicts the error td time units ahead. I am going to explain this particular statement here. So if your error signal is like this, then what would be your PD output? PD means proportional and derivative. So this is the time scale here, and that kpt That means the proportional one would be equal to this one, that is that Kp into T, because this is actually that, say suppose you have taken here the slope we have taken 1, so that is Kpt, and the PD you can see here as et equal to T, that means there would be a jump here, that is Td, and finally this output is actually that PD output, proportional plus derivative. So PD is proportional plus derivative. I am explaining it again. So if your error signal is like this, and if you'd like to only use that proportional control, so basically that output of that proportional controller part, that means again if I draw that block diagram, say error signal is coming here, then it has two blocks, one is that Kp and another one is, suppose this is Kd, or you just put here that Td d by dt. So now if you add these two, so that would be your ut. So here you can see that this one is actually whenever error signal is this one, so here you have that Kp into T, so this one is that one, and what would be that output here, as error equal to 1 T, so then that would be equal to Td. So basically ut equal to Td plus Kp into T. So these things I have plotted here. So there is a shift here, that is the Td shift. So now let us see what happens if we use only proportional controller. So if you use only proportional controller, then suppose this is that time t star. So now at this particular time, if you use only proportional controller, your control input would be that much, this much. But whenever you use PD controller, you can see that this much control input you are getting it here at this particular instant, say t dash. I am repeating it again. So whenever, suppose at t equal to t star, this is that control input because this is ut. If you only use proportional controller, so that much control input will be generated at t equal to t star. But if you use PD controller, you can see that that same amount of control input you get it at t dash. So this t dash, what is this value? This value equal to that Td. So that means it predicts the error Td times unit ahead. So because of this particular control structure, the PD controller, proportional derivative controller, can generate the same amount of control input Td times ahead. So that is actually the beauty of this control structure. And as it anticipates, so anticipates means, you can see here, if I just show a particular diagram, say suppose, so just look at this particular diagram here. So R is that reference command and this is YT. So now whenever time progresses, then that YT is increasing, and you know when YT crosses that R, then that on-off control action takes place. But in this particular case, we are using, say, PD controller. So here I can show you that this is your reference command, and the control output is going like this. Suppose it is going like that. It is a smooth response. It is like this. So then what would be your error signal? So this is YT, and error equal to that R minus Y. So when t equal to 0, your error signal is here, and whenever it is yt is going like this, you know your error signal is coming like that. So this is your error signal ET. So now from here you can see that what is the slope? The slope is negative slope. So whenever output is increasing, when output is increasing, this output is increasing, you see that slope is actually decreasing. And when slope is decreasing, as the derivative control action is like that det by dt, since this slope is negative, so basically this particular part will generate some negative input. That means the effect would be reduced. It would be kp, it would be kpt minus td. So that means it can anticipate whenever output is increasing, as the slope of that error is negative, then that derivative control actions would be negative. Then again, whenever that output crosses that reference command and output is gradually decreasing, and here you can see output is decreasing, so that error is actually with positive slope. So in this case, this is positive slope. So that means the derivative control action would be positive in this case. So it can anticipate, and accordingly it just generates that output. So in industry and in everywhere, what we do, we use that PID control, that means proportional, integral and derivative. So let me draw the diagram here. That is error signal, and say this is that error signal ET, and then this is KP, that proportional controller, and here you have that integral controller, and here you have the derivative controller. So now I have put that KD, that is called the derivative controller gain. So this is that control input UT. So now if your error signal is like that, so suppose this is T and this is that error signal ET, suppose this error signal is going like that, so then what would be your control input from PID? I think you can do it very easily. So this is actually that proportional, sorry, that is actually the derivative part, because error, say suppose this is T, so then that would be KD. And what would be your proportional part? So proportional is KP into, so proportional part is KP into T, so that means it would be like this. And what would be your integral part? Integral part is, you know, Ki integration tau d tau, so that means that would be tau square. So here you can see that this particular action is PD action, this is only P action, and the PID action is the parabolic one, that is PID. So that means whenever you will be using proportional, integral and derivative, then you can see that that is actually that control input that you would have. So the last one, just I want to give you some philosophical concept of that PID, that means how it works. So whenever you use PID controller, so it basically takes care of that past, present and future. How? So suppose this is the time and your error signal is going, suppose it is like that, this is that error signal, this is that ET. So then suppose you are here at T. So now you can see that that integral controller, so basically gives you that integral of that ET, that means it gives you that area under that curve. So this is actually that integral part, this is that integral part. So here you are at T, so that means that integral part gives you the information of the past. Now at T, the value of ET, so the value of ET, the proportional controller gives you that input, that is Kp into ET. So that means the present thing is associated with the proportional controller. And in case of derivative controller, so it actually takes what is that slope at this moment. So that means it just predicts after some time, that means depending on what KD value you have chosen, so then it just takes some value, say suppose T plus TD. So after T plus TD, what would be that value? So depending on that, proportional controller generates some control input. That means the future is associated with the derivative controller. So this is very interesting to see. That means in case of that PID controller, that proportional controller takes care of that present, and integral controller takes care of that past, and derivative controller takes care of the future. So let me summarize what we have discussed today. So that is, we have started that simple forms of feedback, and we have already discussed what is control, what is feedback, what are the effects of feedback in closed loop control. So our discussion today was confined only in this particular block, that is that controller block. And we have first discussed that on-off controller, and then we have discussed PID controller. So in on-off controller, you know that control input is generated based on that error signal, but there are some disadvantages. One of the main disadvantages is, you know, that control output is a little bit oscillatory, and there are other types of control strategies. One is dead zone, another one is hysteresis. In case of dead zone control, we just allow some dead zone, some band, and in case of hysteresis control, we allow that overlap. Now in PID control, we have separately discussed that proportional controller and the derivative controller and that integral controller. And if we use in various combinations like PI, PD, PID, so you may ask if we just use ID controller, but you see there you have to use some gain, otherwise you cannot achieve that performance as well as stability things. And these particular control structures and control strategies would be discussed in detail later by Professor Ghosh, and you will be also learning how to design KP, KI, KD. So I have given you here just a brief idea on different types of control strategies, simple control strategies that we normally use in applications. Okay, so thank you.